Yep.
Marcello, are you ready?
Yes.
Okay. So good afternoon, everybody. Welcome to our webinar. I'm Neda Sadoughi, and I'm speaking from Tehran, Iran. It's an honor for us to have today Professor Marcello Disconzi as our guest speaker in our webinar on quark matter and relativistic hydrodynamics. Professor Disconzi receives his PhD in mathematics in 2012 at the State University of New York at Stony Brook. From 2012 to 2014, he was a postdoc at Vanderbilt University in Nashville. Since 2014, he's assistant professor at the same university. The title of his talk today is General-relativistic viscous fluids. Before starting, let me also add some words to the organization of this webinar. The length of the talk is maximum 19 minutes plus 30 minutes of discussion. It is okay to ask short questions during the talk, but let us postpone long discussions to the end of the talk. And to keep the internet connection stable, please turn off your video cameras. So Marcello, please start.
Okay, let me just set my my alarm here so I don't go over time. Okay, so thanks the organizers for the invitation. I'm very happy to be here virtually. And everything I'm going to say today, I'm going to talk about different results, and there are going to be different bits with different co-authors. But in total, this is joint work with Fabio Benfica, Jameson Graber, Vu Huang, George Noronha, Maria Rodos, Casey Rodriguez, and Yanjian Chao. So what's going on? Okay. So I think this very first slide is probably known to everyone. So I'm going to go over this quickly and just use this more to set up the notation and my conventions. So a relativistic ideal fluid, as the audience probably knows, is described by the relativistic Euler equations, which are written here. So T, curly T, is the energy momentum tensor of the ideal fluid, and J is the baryon current. So my notation is as follows. Rho is the fluid's energy density. Let's see if I can move this out of the way. Yeah. So rho is the fluid's energy density. N is the baryon density. And the pressure is given by an equation of state in terms of the density and the baryon density. So the pressure is a known function of rho and N. So U is the fluid's forward velocity, which is a unit time-like vector field normalized according to this convention, right? That unit N is time-like, where G is the space-time metric and nabla is the corresponding covariant derivative. Okay. So, of course, the Euler equations are very well studied. They are essential in the study of many physical systems in different parts, different subfields of physics, like astrophysics, cosmology, and high-energy physics. However, there are important situations where a theory of relativistic viscous fluids is needed, where you need to introduce a viscosity. So I'm going to discuss two cases where viscosity is important as a motivation for why we care about the problems that I'm going to discuss later. The first example is the quark-gluon plasma. So the quark-gluon plasma is an exotic state of matter that forms when matter deconfines under extreme temperatures and extreme densities. So people are interested in studying the quark-gluon plasma because it's sort of a unique opportunity to understand the behavior and properties of matter under extreme conditions. Extreme conditions here meaning extreme temperatures and extreme densities. The study of the quark-gluon plasma also lets us study what was happening in the universe right after the Big Bang. That's because microseconds after the Big Bang, the universe was filled with matter in the form of the quark-gluon plasma. So that's a unique window that we have in, at what was happening at the very first few milliseconds after the Big Bang. Now, the discovery of the quark-gluon plasma was a big deal. That was named by the American Physical Society one of the 10 most important discoveries in physics in the first decade of the century, and it continues to be a source of many important discoveries. Just to give an illustration, so here you see the cover of some very prominent physics journals, like Nature or Nature Physics, and they're all talking about the quark-gluon plasmas. And I'm also putting here, for illustration, the cover of a popular scientific magazine, also reporting on the quark-gluon plasma. And you see from these dates here that these are all recent things, right? So it's not like the quark-gluon plasma was a big deal in the early 2000s and now it's forgotten. It continues to be a very active field of study. Now, using a combination of theory, experiments, numerical simulation, and phenomenology, the community was able to acquire a very cohesive picture of the quark-gluon plasma. And nowadays we understand that the quark-gluon plasma is best described as a relativistic liquid with viscosity. So here viscosity is very important to describe the properties of the quark-gluon plasma. Another example where viscosity is important is in the study of neutron star mergers. So for neutron star mergers, as is probably known to this audience, the equation of state is still uncertain. We still don't have a hold of the equation of state for neutron star mergers. But in any case, it was commonly assumed that you could describe such mergers using the Einstein-Euler system. Means relativistic Euler equations coupled to Einstein equations. And that's because the time scales for viscous transport to set in, they had been estimated early on to be outside the 10 millisecond range, which is the scale typically associated with damping due to gravitational wave emission. However, these estimates, they have been recently revised by Alford, Bovard, Hanowski, Redzola, and Schwenzer. And their results can be understood as follows. First, they use some state-of-the-art numerical simulation of general-relativistic ideal fluids. So they do simulations of the ideal fluid, and they use that to get an estimate for the characteristic microscopic length associated with the gradients of the fluid variables. So that's like a macroscopic length scale that they obtain from these numerical simulations of an ideal fluid. Then they have a separate argument based on microscopic theory, which they use to estimate the characteristic microscopic scale of the system. And once you have the characteristic microscopic and macroscopic scales, you can estimate the Knudsen number, which is the ratio between the microscopic and the macroscopic scale. And what they find out is that in these mergers of neutron stars, the Knudsen number may not be small in some cases. Now, when the Knudsen number is not small, that tells you that viscous contributions are important. So the punchline of the result is that viscous contributions are likely to affect the gravitational wave signal. So when people are going to be looking at data coming from gravitational waves from neutron star mergers in the future, it's important that the numerical simulations that are used to compare with this observational data take into account viscosity. So these are two examples, the quark-gluon plasma and neutron star mergers, which are, of course, two systems that physicists are very interested in. They are active fields of research where viscosity is important. So that's the motivation. Let me tell you then how to model viscous effects in our fluid. So here I'm writing the energy momentum tensor of a relativistic viscous fluid. And rho, u, and p are the same quantities as before. So the energy density, the velocity, and the pressure. Pi is the projection onto the space orthogonal to u, where again G is the space-time metric. And then you have these new quantities, curly r, curly p, pi, and curly q. And these are the viscous corrections to the ideal fluid. So curly R is the viscous correction to the energy density, curly P is the viscous correction to the pressure, curly Q is the heat flow, and pi is the viscous shear stress. So that's the energy moment tensor. And I'm going to continue to assume that the pressure is given as an equation of state in terms of the density and the baryon density. But for simplicity of exposition, from now on, I'm going to restrict to the case of a barotropic fluid. So I'm going to imagine the pressure is only a function of the density, just for simplicity. Everything I'm going to discuss is valid in the general case, but just the exposition is going to become simpler in this situation. Now, of course, this doesn't define yet a theory because I didn't tell you what these viscous fluxes are. So a theory of relativistic fluids with viscosity is going to be defined precisely by specifying what the viscous fluxes are. And at this point, there are basically two choices we can make. One choice is to say that the viscous fluxes, they are given in terms of the density and the velocity, and possibly their derivatives. So these are going to be known expressions in terms of the density, the velocity, and their derivatives. So the equations of motion in this case are going to be, as before, the divergence of the energy momentum tensor has to be equal to 0, possibly coupling to Einstein equations if you are interested in the case where gravity is also relevant. So the underlying philosophy here is that of a gradient expansion, which means that you think of the fluid equations as arising from a gradient expansion where the 0th order part is the ideal fluid, the first order part, which means when you have the first derivatives of the fields, those are the viscous contributions and so on. And you can make this expansion and truncate at any order. Theories of this type are called first order theories. Another alternative to model your viscous fluid will be the following. You say that these viscous fluxes, they are new variables in your system. They are new variables that are to be treated on the same footing as the density and the velocity. So the equations of motion in this case, they are, as before, the divergence of the energy momentum tensor equal to 0, possibly coupled to Einstein. But then you have to supplement these equations by further equations of motion satisfied by the viscous fluxes. And you can clearly see why that's needed, because if you're now throwing some new variables in your system, these are now new variables, then you need a new equation of motion. Otherwise, you're going to get something that's underdetermined. The underlying philosophy here is that of the method of moments. And theories of this type are known as second order theories. So those are the two big picture type of modeling choices that we can make. So in summary, if you have a first order theory, then a quantity like pi, the shear stress, for example, would be a known expression in terms of the density, the velocity, and their derivatives. And if you have a second order theory, a quantity like pi would satisfy its own separate, newly postulated equation of motion. So those are basically the two choices we have. So let me give a little bit of the historical background. The first theory of relativistic viscous fluids that was proposed is due by Eckert, that was back in the 40s. Excuse me. And later on, there was a very similar theory proposed by Landau and Lifshitz in the 50s. So these theories, they are first order theories that are defined as follows. The viscous correction to the energy density is set to 0, so this term doesn't appear. And then the viscous shear stress and the viscous correction to the pressure are defined by these expressions here. There is also a form for the heat flux, but I'm setting that equal to 0 just for simplicity. Okay, so let's ignore this term for a second. And then in these expressions, you see that you have these coefficients eta and zeta. They would be known functions of the density, which correspond to the coefficients of shear and bulk viscosity. So you think of this as precisely generalizations to the relativistic setting of what the coefficients of shear and bulk viscosity are for the standard compressible Navier-Stokes equations. So, of course, then you ask, why these choices are made. How did Eckert, Landau, and Lifshitz came to these specific choices? There are two basically modeling ideas here. The first is that they were looking for a covariant generalization of the Navier-Stokes equations. And it takes a little explaining, but if you think a little bit about these expressions, you're going to see that they are the direct relativistic analogs of what you see in classical fluids. And the other way that they arrived at these choices is by enforcing that entropy production is always non-negative. So there's this thermodynamic principle about entropy production, and I'm going to say more about entropy throughout the talk. So let me first point out that this seems a very natural choice. The Eckert and Landau-Lifshitz theories, they seem very natural when you first see them, but they have problems, okay? Turns out that these theories, they violate causality, right? Causality, remember, is this fundamental principle of the theory of relativity, stating that no information can propagate faster than the speed of light. And these theories, they violate causality. They allow for faster than the light signals. Mathematically, what is behind this phenomena is that the equations of motion that you obtain from Eckert and Landau-Lifshitz, they are not hyperbolic. They are not hyperbolic equations. So, so if you have something that's compatible with relativity, you need to have hyperbolic equations of motion. Now, the Eckert and Landau-Lifshitz theories, they are also unstable. If you don't know what instability means in this context, think that instability, or rather stability, basically is a type of mode stability. So essentially what you do, you linearize the equations about global equilibrium, and then you look for plane wave solutions. And stability is the statement that these plane wave solutions, they cannot increase exponentially in time. And that's a criteria that fails for Eckert and Landau-Lifshitz. So these are two bad things that these theories have. They are not causal, and they are not stable. Moreover, these are not features that apply explicitly, sorry, they do not apply only for Eckert and Landau-Lifshitz. They apply to large classes of first-order theories. So the underlying message here is that it turns out that it's difficult to construct a theory of viscous fluids that's compatible with relativity and that preserves causality and stability. And if you look at the literature, a great deal of the work in the literature is trying to address this problem of how to construct causal and stable theories of relativistic viscous fluids. So let's move on. So that was the first example, Eckert and Landau-Lifshitz. Another popular theory is the Israeli-Stewart theory that I'm going to introduce in this slide. So the Israeli-Stewart theory starts, as always, with the energy momentum tensor. And this theory actually goes back to the work of Israeli-Stewart. This is going to be a second-order theory, initially introduced in the 70s. But the modern versions, which means the equations that people actually use when they study, for example, the quark-gluon plasma, they're not exactly the equations that Israeli-Stewart wrote down in the 70s. There are some modern versions due by different authors. So all these theories that I'm listing here, the original Israeli-Stewart, the Bayer, Romansky, Son, Steiners, and Stepanov, and the Denikol, Niemey, Molnar, and Rirsky, they're all different theories, but they're more or less similar. So for simplicity, I'm going to refer to all these theories as the Israeli-Stewart theory, although the specific details of how they work are different in each case. So the equations of motion, they look like the following. You have, again, the divergence of the energy momentum tensor is 0. The viscous correction to the energy density is set to 0. And then remember, this is a second order theory. So you need to postulate new equations of motion for the viscous fluxes. And the new equations of motion, they take this form. They take the form of transport equations, where these quantities are defined as follows. Pi hat is the projection of a 2 tensor on the space orthogonal to U, but is the projection on the symmetric and trace-free part. Sigma, that appears here, is the U orthogonal trace-free part of the derivative of the velocity. And you have these coefficients taus, that they are all relaxation times, which are known functions of the density. And then you have these terms J on the right-hand side. I'm not going to write what they are explicitly. There are some complicated terms. But in general, they depend on up to first derivatives of the fields. Now, which terms exactly appear in each one of these J's depends on your modeling choices. But in general, they can depend on up to first derivative of all the fields. So what you see here is that because these J's depend on up to first order derivatives of the field, these are all top order terms, which means that these are terms that contribute to the principal part of your system. So as you can imagine, because these are top order terms, the system, the Israel-Stewart system, is highly complex. In the end, you end up with a very large system that has non-diagonal principal part. So this is, for example, different than what we have for Einstein equations, which is also a large system, but it has diagonal principal parts. So essentially you can think of it just as a bunch of single wave equations. That's not the case here. The system has non-diagonal principal part. So it's kind of like the coupling is really bad. Now, what are some features of this theory? First, stability holds. So the Israel-Stewart theory is a stable theory, so that's a very good feature. And some things know about causality as well. So if you look at the linearization of the Israel-Stewart equations about global equilibrium, that the corresponding linear equations are causal. The global equilibrium is characterized by states where the density and the velocity are constant and the viscous fluxes vanish. So if you linearize about these special states that are called the global equilibrium, the resulting linear equations are causal. Away from linearized theory, if you look at the full nonlinear theory, causality is also known in 1 + 1 dimensions and in rotational symmetry. And finally, this theory, the Israel-Stewart theory, has been very successful in applications to the quark-gluon plasma. So that's the primary theory that people use for numerical simulations and for phenomenological studies. And if you look at the recent book by Romaski, there is a very good account of more or less the state of the art of the field, and it's primarily based on the Israel-Stewart equations. So the message here is that the Israel-Stewart equations are very good for applications, specifically for applications to the quark-gluon plasma. But if you look at this list of good features, there are some things missing here. First, what about local opposedness? By local opposedness, I mean is local opposedness of the Cauchy problem, meaning given initial conditions, does there exist a unique solution to the equations of motion? So there's a problem of existence and uniqueness, which in the mathematical jargon we call local opposedness. And of course, what about causality in 3 + 1 dimension without symmetry assumptions? The causality that I mentioned before was only causality for the linearized equations about these special states. And as you can clearly imagine, knowing that the linearized equations about the global equilibrium are causal, that doesn't tell you anything about causality of the full nonlinear system. And if the full nonlinear system is not causal, then these equations ultimately are not physical, right? Okay, so that's the first result, which is causality and local opposites of the Israel-Stewart equation. That's joint work with Fabio Benfica and Jorge Noronha. And the statement can be summarized as follows. The Israel-Stewart equations are causal. The Cauchy problem is locally opposed, and this local opposedness holds in a class of functions known as Gevrey spaces. Moreover, if the heat flux and the shear stress are absent, we're looking at a simplified case of the equations, then local equipoisance in fact holds in a larger class of function space called Sobolev spaces. And all these results, they hold with or without coupling to Einstein equations. So if you don't know what these function spaces are, let me introduce them to you. Gevrey spaces are function spaces characterized by functions that have a sort of controlled growth on their derivatives. The way you should think of Gevrey spaces is as a generalization of analytic functions. So we have this coefficient s appearing here. If s equal to 1, functions satisfying this property are precisely analytic functions. So Gevrey functions are a generalization of analytic functions. And then Sobolev functions, Sobolev spaces, are spaces of functions where all derivatives up to a certain order are square integrable. So those are the Sobolev spaces. And I'm going to say more about Sobolev spaces later on. Now, how do we prove this theorem? Let me give you sort of the main ideas. If you want to show that a system of equations is causal, essentially that boils down to computing the system's characteristics. You have to look at the characteristics of the system. Now, for the Israeli-Stewart equations, remember I was saying that this huge system with non-diagonal principal parts. So if you simply try to do a brute force calculation of the characteristics, that's intractable. So you need to kind of be a little smarter here. And what we do, we think geometrically. We develop some calculation techniques that are sort of guided by the underlying geometry of the problem. And by the underlying geometry, I mean that we try to find what would be the correct analogs of the acoustical metrics for this system. So if you don't know what acoustical metric is, the acoustical metric is the relevant Lorentzian metric for the propagation of sound waves in the case of an ideal fluid. And it's the same kind of structure that we try to identify in the viscous case. So that's how we find the system characteristics, by thinking in sort of a geometric manner. Then, to prove existence and uniqueness, which means to prove local equipoisance, we derive some estimates using some techniques of weakly hyperbolic system. That these techniques, they go back to some seminal and famous work by Leray and Omia that started in the 60s. And here is where we need to introduce you these functions called Gevrey spaces. That's to avoid the loss of derivatives. When you're going to do estimates, to avoid loss of derivatives, you need to use Gevrey spaces. However, if you look at the simplified case where Q and pi are absent, these estimates actually hold in more generality, they hold in Sobolev spaces. And that's how we prove existence and uniqueness. Okay, so that's all very good. Now we know that the Israeli-Stewart theory is very good for applications, and we know that it's causal in 3+1 dimensions without symmetry assumptions. We know that we have some local equipoisance. However, there are some limitations to the Israeli-Stewart theory that I would like to discuss. The first limitation is that actually it's not known if the Israeli-Stewart equations are the correct model to study viscous effects on neutron star mergers. Well, it's not known in the sense that first, we don't know if it's the correct physical model. But moreover, when you're going to study neutron star mergers, you have to couple your equations to Einstein equations. And the only way you can actually produce information about the system is by numerical simulations, right? There's no way you can get analytic solutions for Einstein equations coupled to Israeli-Stewart. So you have to rely on numerical simulations. And then there's a catch. To produce numerical simulations of Einstein equations actually is not something very simple. There's an entire community in general relativity dedicated to study numerical solutions to Einstein equations. That's a very difficult problem. And in particular, all the numerical schemes that people use, they are constructed for theories that are locally well-posed in Sobolev spaces, right? So the local well-posed in Sobolev spaces enters in a crucial manner to make those algorithms work. So the jargon that people use in the general relativity community is that you need equations that are strongly hyperbolic. However, we don't know if that's the case for Israel-Stewart. Remember, I told you about local opposedness that holds in Sobolev spaces only in the simplified case when Q and pi are zero, which means when you don't have heat flux and you don't have shear stresses. So we actually don't know if Israel-Stewart can actually be reliably simulated when coupled to Einstein. That's a very strong limitation. Another limitation is that even in the case of the quark-gluon plasma, where Israel-Stewarts have been applied successfully in many cases, it is not known if they are applicable to low-energy heavy ion collisions when vorticity effects and the dynamics of the baryon current are relevant. And finally, it's known that the Israel-Stewart, they are not able to describe shocks. And what do I mean by they're not able to describe shocks? If you assume that a shock exists in 1 + 1 dimension, just take the simplest case, 1 + 1 dimension, and you assume that a shock exists, you can prove that these shocks, they are not physically acceptable, in the sense that, if you assume that a physical solution exists, you are able to derive a contradiction. Okay, so there are no acceptable physical solutions, physical shock solutions for Israel-Stewart. So what all this is telling us is that there is a strong motivation to seek for alternatives to the Israel-Stewart equations. Okay, so you want to seek alternatives. And that's what I'm going to spend most of the rest of the talk discussing, alternatives to Israel-Stewart. But before I get to that point, I want to spend one slide talking about this problem of shocks. Okay, because if you listened carefully to what I said, the argument showing that Israel-Stewarts are not able to describe shocks is an argument that's by contradiction, which means it assumes that a shock forms and then derives a contradiction. But there's this assumption, it assumes that there exists a shock. But maybe a shock never forms, and then that assumption would be vacuous, right? So in order to make this argument, to give some teeth to this argument, we have to show that shocks in fact arise. And that's the content of the next theorem, the next result, which is joint work with Wu Huang and Maria Rodos. And this is a result that's something a little more general than shocks, is a result about breakdown of solutions. And the statement is as follows. There exists an open set of smooth initial data for Israel-Stewart equations, for which the corresponding unique smooth solutions to the Cauchy problem break down in finite time. In other words, what we do in this paper, we provide an algorithm to construct initial data that has the following property. At time 0, you start with initial data. Then there exists a unique solution to the Israel-Stewart equation, but this solution exists only up to a certain time t, which is finite. And then at time t, a singularity forms. So there's a singularity. That's what we call a breakdown of solutions. And let me point out that these initial data, they're not something exotic. You can say, okay, maybe if you get something very exotic for initial data, something like this would happen, but this exotic initial data will not be physical. Actually, the initial data we construct is very physical because there are some perturbations of constant states. You start with a constant state and you perturb a little bit in a localized region, and then these solutions are going to become singular. Is that a question? Somebody is speaking? Okay, no, I guess no.
Sorry, do you mean
yes.
by singularities discontinuities that form?
That's a very good question. So let me explain what happens and I tell you about what the singularities, okay? Just bear with me for a second.
Yes.
So the way the proof goes is the following. We use some strategy that actually is well known in this type of work. We assume that the solution exists for all time. Then we derive some quantitatively precise estimates for the evolution of curly P. Remember, curly P is the viscous contribution to the pressure. And then we derive a contradiction, okay? So we show that if a solution existed for all time, you derive a contradiction. So to your question, because it's a proof by contradiction, proofs by contradiction, they always have the following limitation. They do not reveal the nature of the singularity. So all we can say is that a derivative of your solution blows up. So but a derivative in blowing up can happen in different ways. For example, you can have that a cusp evolves, that would give a derivative blowing up, or it could be a discontinuity that also would give a derivative blowing up. So we cannot characterize exactly what goes wrong. We know that something goes wrong if the solution does not exist for all time. But we cannot put our finger and say exactly what goes wrong. And that's because of the method, because it's approved by contradiction. Okay, so we know that something blows up, but we don't know the nature of the blow up. Does that answer your question?
Yes, thank you.
Okay. Okay, so as I said, for the rest of the talk, I want to discuss alternatives to the Israel-Stewart theory. So let me talk about the BDNK theory. The BDNK theory is a first-order theory. So in contrast to Israel-Stewart, this is going to be a first-order theory. And this theory is actually the culmination of several works. There's a series of works by different authors that led to this BDNK theory, which is defined as follows. Again, you start with the energy momentum tensor of a viscous fluid. And then you define your viscous corrections by these complicated expressions here. Okay, don't bother too much about the details of what these expressions are. There is some specific choice for these viscous corrections that is made. And in this specific choice, you see that there are some coefficients, taus and beta, and they are known functions of the density. And these taus in particular, they play the role of relaxation times. Now, if you compare these choices with the Eckert and Landau-Lifshitz theories, what you're going to see is that there are many more terms. We have many more terms here than the Eckert and Landau-Lifshitz theories. And you might ask why? Why makes things so complicated? It turns out that you need all these terms to fix the causality and instability problems of the Eckert and Landau-Lifshitz. So in a nutshell, the way you should think of the BDNK theory is as a fix, or rather the correct way of doing what Landau and Lifshitz, Eckert and Landau-Lifshitz were trying to do. So it's like you want to do a covariant generalization of the Navier-Stokes equations. That's what this is, but it's a correct covariant generalization in the sense that it's causal and stable. And of course, you're asking how do we arrive at these specific choices? So let me say a few words about that. The basic idea is, in hindsight, very simple. The philosophy is that, you see, you have this fundamental principle of causality, right? So we should let the fundamental principle of causality constrain which terms are allowed in the theory, rather than doing what Eckert and Landau were doing, which is start to making choices a priori, and then later on try to establish a causality, right? So it's causality is the fundamental principle that should dictate what the theory can be. And how do we implement this in practice? We do the following. First, we use this idea of effective field theories, right? In an effective field theory, the philosophy is that all terms that are compatible with the symmetries of your theory should be present. So first, we write the most general energy momentum tensor that depends on up to first derivatives of the density and the velocity that's compatible with the underlying symmetry of the problem. And the underlying symmetries in this case are the symmetries of general relativity. Now, when you write this most general energy momentum tensor, you can write all its irreducible components, right? The parts that are, for example, the symmetric trace-free part of the velocity and so on. You can write all its irreducible components. Now, each irreducible component is going to come with a specific coefficient that in principle is undetermined. It's a transport coefficient. For example, for the symmetric trace-free part of the gradient of the velocity that's orthogonal to the velocity itself, you know that this coefficient is going to be the shear viscosity, right? But each irreducible part comes with a coefficient. So when you write this down, you end up with a monstrosity, this huge energy momentum tensor, which has a lot of coefficients, and that seems intractable. So the first thing is to try to reduce the number of coefficients in your theory, and you do that by some physical argument. For example, you can demand that the entropy production is non-negative within the limits of validity of the theory. I'm going to say more about this later on. You can also study some particular cases where the theories were understood. For example, when this theory first came out, it came out in the context of conformal theories. Conformal theories are much simpler, so the conformal limits were understood. So using this kind of physical principles, you can reduce the number of coefficients in the irreducible decomposition of your energy momentum tensor. Once you have this reduction, you have this now energy momentum tensor with a smaller number of coefficients, then you can go ahead and start to look at causality. And for that, you need to compute the system's characteristics. And that's the topic of the next result. So this is a theorem which is causality, stability, and local well-positives of the BDNK theory. And this comes from a series of results in collaboration with Fabio Benfica, Casey Rodrigues, Jens and Chow, Jameson Graber, and George Noronha. So if you put all these different results together, you can summarize them as follows. The BDNK equations are causal and stable. The Cauchy problem is locally well-posed in Sobolev spaces, which means that now given initial data, there exists a unique local solution that belongs to some Sobolev space. Moreover, these results hold with or without coupling to Einstein equations. So how do we prove this? First, there is the causality, and that's similar to what I mentioned before for Israel-Stewart. You have to look at the system's characteristics. For that, you have to think geometrically, because even after doing the reduction that I told you about based on physical principles, you still have a lot of transport coefficients, and this is intractable to do this by brute force. So you have to think geometrically. Now, for the stability, that's very complicated because we have to look at the roots of the polynomial equation that defines the modes for the linearized theory. So that's a very high-order polynomial, so there are no explicitly expressions for its roots. So what we do for that, we prove some general stability theorem that basically says that if a theory is causal and it's stable in the fluid's rest frame, then it's stable in general in any frame, provided some structural conditions hold. Of course, the structural conditions that I'm referring happen to be satisfied by this theory. Okay? I mentioned the stability in the fluid's rest frame because that's something you can actually compute. Because if you look at the fluid's rest frame, this polynomial equation that defines the modes simplifies considerably. And then for the local well-posedness, you run into this problem that I mentioned before that is similar to what happens to Israel-Stewart, that the equations, they are not in diagonal form. The principal part of the system is not diagonal. So what you do, well, then you try to diagonalize your system. And we can actually do that because we understand the characteristics of the system very well. To diagonalize the system, you need to understand its characteristics, and that is done in the causality part. So once you diagonalize the system, then you can prove something. And the way that goes is the following. The diagonalization actually happens at the level of the principal symbol of your system. So the principal symbol involves some rational functions. So when you rewrite this as a PDE, it is no longer a PDE, it's actually a pseudo-differential equation. So your diagonal system is not a system of partial differential equations, it's a system of pseudo-differential equations. So when you do that, you have to do pseudo-differential calculus, and you're running some technical problems here because these are quasi-linear problems. So the standard textbook pseudo-differential calculus that you find in textbooks, it's developed for systems that are not quasi-linear. It's for linear systems. So here we have to do some pseudo-differential calculus for quasi-linear systems, which means symbols with limited smoothness. But anyway, that's something we can do, and that's how we prove local well-posedness. Now, let me mention that, as I said before, I was illustrating everything using an equation of state that was barotropic, but this result and everything that I said actually holds if you have a baryon density. So it actually holds in the general case. Okay, now there's an obvious question here. You can say, okay, this is very nice. You wrote this theory that's causal, is stable, is local opposed. But you can always write down equations that have all these properties and claim that that's a physical theory of fluids, right? But to know that that's an actual physical theory, you have to connect with known physics. So that's the topic of this slide, how we connect the BDNK theory with known physics. First, we show that the entropy production is non-negative within the limit of validity of the theory. I know that I keep saying this, but I'm going to explain this in more detail later on in the next slide. So let me skip the entropy production statement for a second. Something very nice happens. This BDNK tensor actually is derivable from kinetic theory. So it has an underlying microscopic foundation for this tensor. That's not true for the most general case, but it's true in some special cases that are already of physical significance. For example, if you look at the case of a barotropic equation of state, then the BDNK theory is derivable from kinetic theory. So it has an underlying microscopic foundation. And we can also do the following. We can also look at some test cases. There are two very well-known flows in the study of the quark-gluon plasma, which are called the Bjorken and Gubser flows. And for these flows, the behavior of the fluid is well understood. So we can test what the BDNK theory says about these particular flows and see if it agrees with what's well known in the literature. And here's the illustrations. So for example, for the Bjorken flow, it's known the Bjorken flow has a hydrodynamic attractor, which happens also for the BDNK theory. So these curves, they're all curves showing solutions for the BDNK theory using different initial conditions, and they all converge to some attractor solution. Another example is in the case of the Gubser flow. So for illustration, here I'm plotting the temperature profile of the Gubser flow. Rho here is some new variable that you do after some field redefinitions. So rho is not the density. And for illustration, I'm plotting here in blue, this blue curve. I don't know if you can see in my screen, but this blue curve is the Gubser flow for the Landau theory, the one that's not causal. And you can see that because this theory is not causal and is unstable, you have some pathologies happening for the temperature. The temperature actually becomes negative, so that's not physical. Then on the dotted curve, the dotted black curve, that's the ideal fluid. So you see the ideal fluid has, as expected, a good behavior. The temperature is non-negative. And the red curve is the BDNK theory. So the BDNK theory, you see that it does not suffer from this pathological behavior that the Landau theory has, where the temperature becomes negative. So all in all, the BDNK theory, it has all the good features of the Israeli-Stewart theory, plus a good local well-posedness theory in Sobolev spaces, which is something lacking for the Israeli-Stewart theory. Okay, and I can't stress this enough, right? So if you want to study viscous effects on neutron star mergers, you have to simulate Einstein equations coupled to your fluid equations. And then you talk to the people in the numerical general-relativity community, they're going to tell you that they want to simulate things that are strongly hyperbolic. Okay, so you need a strongly hyperbolic, which in particular entails local well-posedness in Sobolev spaces. And that's not known for the Israeli-Stewart case, the Israeli-Stewart theory, except in some particular cases I mentioned, except when pi and q are 0. But that is actually known for the BDNK theory. Okay, so that makes the BDNK theory actually a very good candidate for the study of viscous effects on neutron star mergers. Now, finally, I kept promising that I would say something about entropy production. So let me say a few things about entropy production. And you can write the first law of thermodynamics. So you can define the entropy gradient, this quantity S mu that's defined here. And T is the temperature, and mu is the chemical potential. And there is some known thermodynamic relations that hold between these quantities. And then to talk about the production, I need to introduce a power counting scheme. So remember that the underlying philosophy for first order theories is the philosophy of a gradient expansion. So when you do a gradient expansion, you have to organize things in a scale. And the way you do this is by introducing a power counting scheme. And the power counting works as follows. A field itself has order 0, which I write as order 1 because that means, like, you know, from the point of view of the power counting is like a constant, right? So it's order 0. Derivatives of the field, they have order 1, so I write as order of a derivative. And second derivatives, they have order 2. That's your power counting scheme. And then when you have products, you simply add the orders. So for example, something of order 1 times something of order 0 is going to have order 1. But if you have a derivative square, that's order 1 times order 1, that's going to have order derivative 2. So that's going to have order square, which is the same order of a second derivative, for example. So that's how your power counting scheme works. And then here comes the crucial observation. Because this is a first order theory based on this gradient expansion philosophy, when you measure things, when you look at the entropy production, that can only be accurate within the limit of validity of the theory, which means that the entropy production, which is the divergence of the entropy gradient, can only be correctly determined up to order 2. Anything that's beyond order 2 is going to be outside the limit of validity of their theory. So your statements have to be restricted to up to order 2 terms. And that's a crucial observation that was first made very clearly by Compton in one of his papers. So if you follow this philosophy, you can compute the divergence of the entropy current. And then on shell, which means for solutions of your equation of motion, you find it's given by this expression plus terms of order 3. But remember, terms of order 3 are outside the limit of validity of your theory. So these are things that you drop out of this computation. And then when you drop these terms out, what you're left with, you see, are terms that are always non-negative, because sigma is orthogonal to u, so this is non-negative, this is non-negative, and this is also something orthogonal. This is projecting the gradient on the orthogonal to u, so it's also non-negative, so the whole thing is a sum of non-negative terms. Assuming, of course, that the coefficients of shear and bulk viscosity are non-negative, which is a standard assumption. So let me make a comment here. This is one point where the BDNK theory differs fundamentally from the Landau, Lifshitz, and Eckert theories. One of the problems with the Landau, Lifshitz, and Eckert theories that leads to these issues with causality and stability is that they try to construct an entropy production that was always non-negative for all orders in the gradients. But that's asking too much, because your theory has a limit of validity, and you impose something that's something that goes beyond the limit of validity of the theory, which goes something that goes for all orders in the gradients. You are putting constraints which are too stringent. You are putting constraints that are too strong in your theory, and that's one of the things behind the construction of the energy momentum tensor for Landau, Lifshitz, and Eckert that eventually leads to instability and lack of causality. Okay, so let me finish. I want to try to stay within an hour so that we have time for questions. Let me finish with some future directions of research. What where can we go from now? First, we'll very much like to prove local opposedness for the Israeli Stewart theory in Sobolev spaces. remember, I told you that's known only in the particular case where pi and q are absent. But of course, we want to use this Rao-Stewart theory also for the simulation of neutron star mergers, right? In the end of the day, we don't know which is the correct model for studying neutron star mergers, if it's the BDNK theory, if it's this Rao-Stewart theory, or some other theory. So you want to have an array of possible different theories for which you can run these numerical simulations. And for all these theories, as I said, you want to run numerical simulations of the fluid equations coupled to Einstein equations. So you want to have strongly hyperbolic theories. So in particular, you want a theory that is locally well posed in subordinate spaces. Now, there's something that I kind of put under the rug when I was talking about this local well posedness business, is that yes, you want something that's local well posed in subordinate spaces, but actually you want more than that. When you're going to run your numerical simulations, typically you do not use the equations of motion as written in their original form. You want to rewrite the equations of motions using some special 3+1 decomposition, which is well adapted to these numerical schemes that people use in the relativity community. So, both for the BDNK theory and Rao-Stewart, if you can prove it's local well posed in subordinate spaces, we would like to have this 3+1 decomposition. That's not something that has been done yet. We also would like to understand shocks in both the Rao-Stewart and BDNK theory. As I mentioned, there is this blow-up result for Rao-Stewart theory, but we actually don't understand the nature of the blow-up, as I was explaining. And of course, that's for one particular class of initial conditions. You would like to study the possible formation of blow-up or shocks for more general initial conditions. And eventually, we would like to add electromagnetic effects to both theories. We would like to study the magnetohydrodynamics version of Rao-Stewart and the BDNK theory. And these are just some possible questions you want to understand. Of course, there are many more things we can try to investigate. So this is sort of a kind of rich field of research where there are many things to be done in the near and medium-term future. Thank you for your attention. That's it.
Thank you. We have time for questions. And
can I ask a question?
Sure.
Yes.
Can you go back where you compare your theory with Gubser and Bjorken flows?
Uh-huh.
So what is the point of that slide? I couldn't understand. What are you trying to show in here?
Well, I'm trying to show that, so we have this theory that have all these good features, right? Causality and so on. But, if it's not difficult to write down equations of motion that are causal and stable, right? So I can just write down some equations of motion and say, oh, this is the equation that describes a fluid, right? That's not going to be true. I mean, you have to actually connect with some known physics. Now, one thing that's well understood is the behavior of this Gubser and Bjorken flow. So one thing you can do, you can take the BDNK theory and see how this theory behave for these specific flows, and see if they reproduce some features that are known for these flows. And two features that are known for these flows are the existence of this hydrodynamic attractor for Bjorken, and the fact that temperature profile has pathologies if the theory is not causal, right? So there are these.
So what do you mean by hydrodynamic attractor in Gubser flow here, or in Bjorken flow?
I mean that if you start with very different initial conditions, so these curves are all different initial conditions. There are all solutions with different initial conditions, and you see that they all converge to the same solution as time passes.
But in W coordinate, right? W means here.
Yeah.
But not in tau, in the original Boltzmann. You're saying that here so this is the toy model. This is not really so we understand this is not the Bjorken flow itself. I mean, this is just a toy model.
This is the toy model, yeah.
Yeah. So you're saying that I'm comparing to this and I'm finding the same type of behavior, like, but numerically. You're not doing this.
Oh yeah, numerical. This is numerical, yeah.
All right. Thank you.
You're welcome.
Giorgio, please.
Oh, okay. Hi. Thank you. This was a really great talk. Just sort of as a
thank you.
as a sort of comment. I mean, one thing that I think it's sort of should be added is, I mean, hydrodynamics is an effective theory, and it's an effective theory of statistical mechanics. So somehow in every volume element, you have microstates. It's not a theory of the Boltzmann equation. It's a theory of, in every volume element, microstates are maximized, but the energy budget of every volume element is slightly different, and volume elements interact, but the number of microstates are maximized.
Mm-hmm.
From this point of view, Israel Stewart, I'm sort of latching into a talk in the seminar series of a couple of weeks ago by Lorenzo Gavassino, that if from this point of view, Israel Stewart sort of makes sense in the sense that we know from non-equilibrium statistical mechanics that there is relaxation and dissipation. You take the system out of equilibrium, it dissipates. It also fluctuates, and fluctuation and dissipation are not in equilibrium, and this is missing from Israel Stewart because entropy is also monotonically going up. So there is fluctuations and no dissipation. So there is no fluctuations and dissipation, but it's sort of half the deal. And you can sort of see where it comes from, and you can even relate it to, more formally, you can construct Kubo formula for relaxation and such. For first order theories, as far as I can see, the connection to elementary statistical mechanics is sort of missing, because these variables become sort of variables. You see what I mean? I mean, they're not really related to microstates. Yes, entropy is put in, is fixed to be negative. But I do not see, for example, Kubo formula, the effect of fluctuations and things like that. You see what I'm saying? I mean, is this, well, do you think this is coming, or is it?
Yeah, I think this is coming. I think this is something that we are thinking about, but I can't make any definitive statements at this point. But yeah, so probably that's something maybe for my next talk I'm going to add to the last slide as things to be done in the future.
Mikhail.
Hi, thank you also very much for the very nice talk. Actually, I have a question directly regarding the slide which is shown right now. So you're showing the results from the BDNK theory for Bjerken and Gabser flow. What if you compare your results with results from Israel Stewart theory, taking into account, I don't know, various extensions or source terms which are possible in the Israel Stewart theory? How would those test cases compare?
Well, we haven't done that, so I can tell you again. Another question I cannot give a definitive answer. So I don't know. I mean that's something that could also possibly be done, but one of the things that I want to emphasize maybe here is, like, of course, time is finite, so I have to more or less choose which problems to work on. And one of the main motivations for us is really going after the problem of understanding viscous effects on neutron star mergers. Okay, so that's where we are putting a lot of the efforts for this BDNK theory. And so we use like the minimum of the QGP, the quark gluon plasma, just as a test case, just to make sure that you're not starting with something and spending time on something that in the end is completely unphysical, right? So that's why these test cases are there. But we haven't done what you suggested. That's something that could possibly be done, and maybe there are people in the audience that are interested in doing that. The questions are in the paper, so anybody can write down and do these numerical simulations. But a lot of the things, let's say if neutron star mergers was not in the picture, probably would be doing this. That would have been done already. We'd be kind of going after all these possible cases related to the quark gluon plasma. But we're really thinking, of the neutron stars mergers scenario. So that's where our current efforts are. So sorry, I cannot give a more definitive answer to this question either.
Yeah. Yeah, thank you still very much. Actually, my question was less directed into the exact outcomes of those test cases, but rather in the differences which might appear between applying BDNK and Israel-Stewart. But yeah, thank you.
Yes, absolutely. I mean, that's something that can and should at some point be done. Look at these differences, right? But we are not quite there yet.
May I give a comment on this question?
Mm-hmm.
I think we have done some comparison between the BDNK's solution in Bjorken case with the MIS. And also there exist other works by Borkowski and others about that, but we are using two different setups. Something that comes to mind is that in MIS formalism, you have some sense from the microscopic theories. I think this was also George's question about the transport parameters, for example, the relaxation time. But in the case of BDNK, these new parameters, I mean, for example, the parameters that appear in the viscous flux in epsilon and p are, I don't know if there is any physical understanding of them. We can something, I mean, can we find some clue for the values?
Yeah, there is, if you look at the barotropic case where we derive things from kinetic theory, right? In fact, so of course, when you have things from kinetic theory, you have to do some matching conditions. And then precisely what you're saying appears there in the match conditions, because when you do the match conditions, there are some choices that have to be made, right? And the way that these match conditions work to the range of values of these coefficients, of these transport coefficients where causality holds, tells you that certain tensor contractions have to have some properties. Okay, I can't get into the technical details now. I can maybe show you this in the paper later on, another opportunity. But there is this connection with kinetic theory, which is important, right? Again, that's not for the most general case. That's for the case of the barotropic equation of state. But that's sort of a hint of where this physics is coming. And again, you have to keep in mind this fundamental principle of causality, right? So causality is something that that's my take, at least, that causality has to be respected. And once you impose that causality is respected, these transport coefficients have to be in certain ranges, and that tells you something about how the matching conditions have to work when you look at this coming from kinetic theory.
I think George
May I make a question / comment? Good morning, afternoon, evening. Can you hear me?
Yes. So yeah.
Thank you for the very nice talk. It was very interesting for me, even if I missed the first part. I was late. Sorry. I just wanted to understand, because you made a comment about the fact that the direction is to go towards neutron star mergers. So yeah. I have made a talk a couple of weeks ago, and I made also a comment about the problem of neutron star mergers. And actually, in neutron star mergers, it is quite well known that the correct model for at least bulk viscosity is Israel-Stewart, in the sense that they have shown, you can see mathematically, there are nuclear physicists who have made calculation that you really need that time, that relaxation time of the bulk viscosity of Israel-Stewart. And there are also situations in which the system resonates with the proper time scale of relaxation of the bulk viscosity of Israel-Stewart. So I would like to understand if you are trying to reproduce also this kind of mechanisms.
Well, the BDNK theory has these relaxation time mechanisms, right? So that comes in the way its coefficients tau play a role. Now, I'm not going to get into the discussion, but I wouldn't take for granted that it's known that Israel-Stewart is the correct theory for neutron star mergers. I spoke with a lot of people who do high-quality numerical simulation of neutron star mergers. And again, I'm not a numerical person, so I can only report on what I heard from some of the people who work on this. And from all the people that I spoke with, the consensus seems to be that not so much that they know that Israel Stewart, that so far Israel Stewart was, like I say, the only game in town, basically, right? But that people still don't know what in fact, as I said,
because for example, sorry,
can I finish this?
Yes, sorry.
So in fact, the very idea that viscosity is important is quite recent, coming from this paper that I mentioned before. People are not even looking at the viscous effects very carefully on this, and the question of what the correct theory is, in the end, is an empirical question. You can only decide that once you have data. People don't have enough data yet to really start doing the fine comparisons between theory, numerical simulations, and observation. So I think that's still an open question.
Yes, somehow, but the point is that we know the origin of bulk viscosity there, and this beta processes and the deviation from equilibrium of beta processes. And then you can show mathematically that in this case, you have analogy, that the system is identical to Israel-Stewart.
What do you mean by identical? What do you mean by identical?
That if you go to the limit of small deviations from equilibrium, then the evolution, also when the system is fast, so also when you go to the regime in which you need to include the relaxation times, the behavior is the one of Israel-Stewart, because you can map the system into Israel.
Well, let me tell you why that cannot be exactly the case. Because when you say the Israel-Stewart, there are actually different, as I mentioned, different Israel-Stewart theories, right? And like in everything, in this case, the devil's in the details, right? So the dynamics are actually different if you use, let's say, the original Israel-Stewart formulation from the 70s, or the BRSSS formulation, or so on. These equations are actually different, and the evolution is going to therefore be different. The fact that you have some general physical principle that's common to all of them, which seems to be what you're saying, that's what you see in Israel-Stewart, is possibly correct. But the same general principle, which is essentially the fact that things have a relaxation from towards equilibrium, that's also true for these causal first order theories. So I really don't see, without getting into the details of the actual numerical simulations. And
if you want, I may send you my paper. It's a bit long and probably heavy, where there is a discussion about it.
I'll be glad to take a look at it. Yeah.
Okay.
Yeah. So can I just make a comment here for Lorenzo? So the thing is, if you're thinking about, so as Marcello said, this first order theory will have exactly the same behavior. So in fact, if you think about as fluctuations around equilibrium, so that defines the thing that is like the Green's function. The Green's function that will show up for the bulk channel has the same structure, exactly the same structure, the same sort of poles. In fact, BDNK and Israel-Stewart at the linear level, they're basically the same thing. Very, very similar theories. So there's nothing that is in one that is not going to be in the other in that case. Of course, no, linearly, things are different. They deal with the variables differently. That's why at least it has been easier to prove things for BDNK and not for Israel-Stewart in the full nonlinear regime. But linearly, it's the same thing. You have a set of hydro modes, a set of non-hydro modes. The non-hydro modes are the ones that define these relaxation times. They appear in the retarded Green's functions. They define frequency-dependent transport coefficients like eta, zeta, shear and bulk viscosities and connectivity. They will have, you can define a thing like a zeta of omega and k, just like you would do for Israel-Stewart. There really wouldn't be any difference. So I don't think that is an argument to exclude those theories. There could be, of course, that there's another argument that excludes either one or the other, or both. That would be great. But I don't think that is the point yet, at least as far as
Okay, perfect. That was basically my question. Thank you. That clarifies a lot.
Okay, so let me just add to what George said, that the fact that some of the things probably are not clear and people are asking these questions because, of course, it's part of our fault, because we have known these things for a while, but we haven't yet published. For example, none of these papers that we have out, none of them they have like a detailed treatment of the Green's function, for example, right? And again, time is finite, right? But eventually these things are going to be out, and then you can take a look at this.
No, but that's very good, because it was important to see if that kind of behavior can be reproduced.
Right.
Because because we know that kind of behavior is what nuclear physicists give us, and there are all those resonances and so on. So knowing that these theories can do that, it's very important. So thank you for the comment.
So can I ask you something, some follow-up question? So why not simply just prove that there is a pullback attractor that's exactly like, Israel-Stewart theory's pullback attractor? Why are you trying to just compare this to Bjorken while you know that this theory is not the same as Bjorken? That would actually answer the question that, I'd be sure that the two theories are kind of like, similar. Israel-Stewart and BDNK theory.
That's a possible idea that we haven't done. But one thing to keep in mind here is that I think if you try to focus too much, let's say, on Bjork or even Gubser, in this case the flows are significantly simple. So I don't think you're going to kind of. So there are two things that can happen in these cases. Either you get something like a Landau, where the theory is not physical, or if the theory is physical, it's going to pretty much agree with what is known, because there isn't much room to get something different here, because these flows are very simple. That's at least my intuition.
No, but you have to prove it mathematically that there is.
Of course.
These are simulations. I'm sure that there is some similarities, but as far as you want to do a comparison between apples and apples, you better do this with something like Israel-Stewart theory, just not like Bjorken, because Bjorken, as you said, is much simpler.
Oh yeah, absolutely.
But Israel-Stewart in the Bjorken case, Aliraza.
No. W. What I mean is, in W coordinate, you're showing here. This is like the comparison between apples and bananas. You're showing W coordinate here, and you're saying there's a hydrodynamic attractor, but what you're showing is that my theory somehow has the same behavior as this, Bjorken flow in W coordinate. But what you should do is you should show that in Israel-Stewart theory, when I have, for instance, a pullback attractor, that same pullback attractor can be found exactly in your theory. That's what I'm saying.
Yeah, I mean, I think for Bjorken, in the Bjorken flow case, that's at symmetry, right? So once you define the Bjorken symmetry, I think this could be done. This was not done, but in general, if you try
in W coordinate only.
Yes.
Yes.
But if you try to do that away from symmetries, imposing Bjorken or Gubbs or any type of symmetry, then as far as I can tell, no one has even been able to prove that, even for Israel-Stewart itself, right? If you remove any symmetry assumptions.
Yes, you remove the symmetry, but what I'm saying is, that then you see the hole in the argument that you should not compare to Bjorken if you want to really prove that there is some sort of physics backing it up, because this is Bjorken.
You mean this is so what is comparing is Israel-Stewart theory undergoing Bjorken flow and the BDNK theory undergoing Bjorken flow. Those are the two things that he's comparing.
But in W coordinate, right?
Yes.
But I asked this question earlier. I said that this is not the right comparison. If you want to compare to physics, you better do it in tau.
Oh, okay. No, sure.
Yeah, so we could possibly.
But it'll be very similar. I mean, we haven't plotted that. In fact, we actually have. So Arpan Das is here in the audience. He can tell you. We actually were able to map, in the case of Bjorken flow, we can actually find solutions and map one problem to the other. So those things are, in a sense, for very limited cases, understood.
But let me make a comment about the W coordinates. I think that there is this issue that, again, these are test cases, right? So suppose that you look in W coordinates and you see something completely different than what you should be seeing, right? So then that's saying that your modeling choices probably are not correct. I mean, I'm not, at no point I made a claim of this is a kind of exhaustive study of how these equations behave in the Bjorken flow. I'm just saying that these are some test cases that at minimum have to be satisfied for this flow. That's all we're doing. And again, we can spend a lot of time studying BDNK equations under different flows and in the context of the QGP. But that's not exactly what we're looking after. We're just looking at this test case as a very basic threshold.
Just as a sort of, can I, as a physicist, so in the Euler equation, you can put the Euler equation in a Lagrangian form, which which is nice because you can count degrees of freedom, and then you can map, at least linearly, you can map the perturbations into local Lagrangian coordinate transformations. So you have compression waves, which are parallel to some direction, you call them sound waves, and perpendicular waves, which are vortices. Israel Stewart, if you put in Israel Stewart, I mean, I'm sure you know this. I mean, you can do Lagrangians for dissipative systems, and we've done this. What happens basically is that you put in an additional mode. You put in a non-hydrodynamic mode, where basically you have the Lagrangian coordinates and you have the things acting on the Lagrangian coordinates that break isotropy, and they are fluctuations of p mu nu. And I guess, I mean, Lorenzo can correct me, but I guess what he was talking about when he was talking about experimental signatures of Israel Stewart was this sort of non-hydrodynamic modes. Is that correct? Or am I misinterpreting you?
Yes.
You have these additional degrees of freedom. In the case of first order theories, what you have instead is you have a violation of isotropy at the level of the definition of U mu. And then you can sort of shuffle around degrees of freedom for initial conditions because you need to put in the initial data for U mu. This is why I was interested in fluctuations. I mean, do you still have, what do you call a non-hydrodynamic mode for a first order theory? What would you call that?
It's the same definition, right? So when you look at the dispersion relations, right? So are the ones that that survive in the limit omega to 0, right?
Sorry?
It's the same definition. You look at dispersion relations, right? So you have like the sound and the flow channels, right? Where you look at dispersion relations, that there are the terms that go to 0 with omega going to 0, and then there are the terms that do not go to 0 with omega going to 0. The ones that do not go to 0 are the non-hydro modes. So in terms of the definition, is the same.
Okay.
But you see, let me make a comment on that. I think it's important. Of course, you want to look at the mode and you look at the linearized theory. But if you want to really understand the propagation within your system, the linear theory is not the correct guide. You have to look at the fully nonlinear theory and look at the characteristics. The characteristics are sort of the integrated version of the modes, right? So they are the ones who correspond to the actual speeds of propagation in your system for the full nonlinear theory, right? So you can imagine. So if you imagine your theory as coming from some expansion, at each level of your expansion, you can think of this as a linear theory. And if you sum things over all degrees, then you recover the nonlinear theory. So if you think from that point of view, then when you're summing over all the modes of the linear theory, you're essentially kind of reconstructing the characteristics of your system. That's kind of a very, very heuristic way of saying, but I'm just trying to make the point that if you want to understand the propagation modes of your theory, you should really think in terms of the non-linear theory, right? So that the linear theory is not going to give you the whole story.
Hello. Hi, can I make a comment about, because there was a lot of discussion about equivalence between Israel-Stewart theory and the first order theory. So in general, definitely that Israel-Stewart theory, the number of evolution equation and the number of evolution equation in the first order theory are different. So in general, may not be it is possible to show that both the theories are same. However,
that doesn't claim it. That doesn't claim it. It was claiming something about the linear part of the theory, like when you look for the Green's function and things like that, right?
Yeah. No. So I wanted to stress that there are some limiting case. As for example, if you consider Israel-Stewart theory with a constant relaxation time, then there are possibility that you can actually map this first order theory and Israel-Stewart theory one-to-one. So that means the number of equations will be same in both the theory, and there will be a one-to-one correspondence between the evolution equation. So that we are able to show with George in one of the paper for massless particle at least.
Mm-hmm. Yeah, I'm aware of the paper that you're mentioning. Yes. Now let me just add a comment to that. So the fact that they are not the same theory, I think, is like the whole point, right? Because if they were the same theory, then you know we're not going to be doing anything new. We actually want, and if possible, more theories that are different. Because again, once people start getting data from neutron stars, we want to kind of have like a robust and framework, right, where we can see what is the best way of describing these mergers, the viscous effects on these mergers, right?
But I have a one general question is like this also have my confusion is that if you are talking about a general fluid velocity frame, then you have various coefficient coming in your.
Sorry, I couldn't hear which coefficients.
So like the coefficient which are sitting in front of the derivative expansion.
Okay.
And physically we have a notion of different viscosity, say shear viscosity or bulk viscosity. So how in a physical theory how one can map from this coefficient with the actual viscosity one-to-one?
Well, that comes from what I was mentioned before, the matching conditions, right? Now, from the point of view of the gradient expansion, we have all these coefficients, right? And formally, there is no reason to say that one coefficient is more important than the other, right? So it's just that some of these coefficients, they are kind of more, let's say, familiar to us, like bulk viscosity and shear viscosity, but in principle, they are all there in the gradient expansion. What happens is that in theories like in the Landau, Lifshitz, and Eckert, you don't see those other coefficients because some specific choices are made to kill those terms, right? But now we know that those choices are actually the wrong choices because then they lead to something that violates causalities. And that goes back to the principle I was saying, you keep all these coefficients, like think of this as coming from this gradient expansion, and causality is going to tell you which coefficients are important or not, right? And if causality tells us some coefficient which is not shear and not bulk has to be there for causality, you have to take that as something physical, right? Because causality is a physical notion. So in a certain sense, if you want to try to interpret what these other coefficients are, you could think of them as, let's say, some kind of regulators, right? They're kind of there's some kind of regulators that have to be there to enforce causality, right? But I agree with you that the sort of vanilla physical interpretation of what these coefficients are is, of course, not clear as something like what bulk or shear viscosity would be.
Yeah, I mean, in one of the paper, what Koptun published is like he could show that by choosing some specific frame, either Landau frame or the other one, then you can definitely you can make this combination of different coefficient and you can just map it to this standard viscosity, say eta or zeta. But for a general choice of u mu, I mean, not choosing like a Landau frame or the other one, just a general u mu, is there a possibility that one can always say that, okay, this combination will give you this viscosity and this combination will give you some other viscosity, something like this?
Yeah, for shear bulk, yes, right. And in fact, in our paper, in our latest paper, we write explicitly like the bulk viscosity would be like a given combination of the coefficients. If we start just writing things like just labeling the coefficients, let's say A1, A2, A3, then there's a specific combination that corresponds to, let's say, to bulk viscosity. So that's that's true in general. But the point is that you're not going to be able to map everything to just shear and bulk. You're going to still be left with some coefficients, right? And those coefficients need to be there for causality to be respected.
Okay.
George, please go.
Yeah, so it's just the two comments. So this first one about what Arpan just said. So what Marcello said is correct. And also just remember if Israel-Stewart theory was formulated in a general frame, you will have a lot of coefficients as well. The thing is that you only see it in Landau or Eckert or something like this, but the same thing, the same ambiguity that appears when you define local equilibrium, the root of this multiple coefficient appears everywhere. It will appear for Israel-Stewart as well. And if you do it, you will see a bunch of new coefficients, just like it happens in the other one. In fact, it will be probably worse. So this is something that should be done. And I urge someone to just sit down, go to kinetic theory and rederive the whole thing in a more general frame for Israel-Stewart. That'll be great to see. The other comment is a quick comment about the first order. So remember, these first order theories, they have one derivative in the t mu nu. So when you take a derivative, they are second order partial differential equations. You can always invent a way to write a second order system in terms of first order systems, right? So in a sense, you can create, if you want, a version of this that looks like Israel-Stewart in the sense that you only see first order derivatives of things, right? So in fact, in our paper, in our most recent paper, when we talk about general relativity, we actually use such a first order redefinition to prove things because it was useful, but you can just do that. So it will be something that is not going to be exactly like Israel-Stewart, but it will have the same sort of structure. The derivative of some new field plus the new field equals something that it relaxes to. It'll be the same thing. So you can actually do that, but the form itself is different. And I don't think anybody actually studied this in detail.
Yeah, so let me add a comment to that. In fact, when I was mentioning at the end that for numerical simulations, you actually want to see, you want to write the equation as a 3+1 decomposition. These actually are 3+1 decomposition for the equations written as a first order system, right? So you rewrite your system of second order partial differential equations as a system of first order equations. And it is on this system of first order PDEs that you want to do a 3+1 decomposition. So that's and that's true not only for the fluid, but for the Einstein part as well, right? When you do these numerical simulations, so all these methods that people use for numerical simulation of Einstein equations, they write Einstein equations, which originally is written as second order, they write as a system of first order equations. So Masoud, I think we have, do you have questions on the chat? I just see the chat popping up.
Yes, yes.
But somehow I can't open the chat here. Let's see, maybe it's because I have, just a second.
May I ask a question based on the comment of Professor Noronha about the fact that you start from a second order and you go to the first one. So do the number of degrees of freedom of Israel-Stewart and the ones of the first order theory match?
No.
Because, yeah, indeed, because I was making a counting. So for the first order, they should be 10 because you have, but for the Israel-Stewart, they are quite more.
Yeah, they don't. And of course, that's something that can be an issue, for example, for initial conditions, right? There is, and of course, if you want to compare both things, ideally you would like to compare things with the same initial conditions, but you can't because the number of degrees of freedom is not the same. So in one of our papers, I don't remember which one now, we actually have some discussion about initial conditions where there is sort of a way of what to be, like, say, the best choice that you can make of initial conditions for the BDNK system that will get you the closest to what we would have for initial conditions for the Israel-Stewart system, and that will probably what you want to do if you want to compare things. But you're right, they don't match.
Okay. Thank you.
So let me just run through the chat really quick to see if there's any question here. Okay, I think people are just talking to each other, and there's no question directly here. Okay, sorry. I just want to make sure that they didn't miss any questions from the chat.
Yes, this was a discussion on the chat, and I said that a lot of young people are here to work on different problems, but I'm not young. Just kidding. Okay, I have a question myself.
Mm-hmm.
One question. Whenever you were talking about global equilibrium as something that I understand as a hydrostatic configuration. Yeah. What happens if we have a rigid motion and then perturb it? What happens to the modes?
Well, a rigid motion means like a Lorentz transformation?
It's like if we have this beta, which is u over t as a Killing vector, and then we can have a rotation, for example, but we still have the equilibrium. Okay. What I mean, if we assume that that kind of equilibrium, and then go for the modes, for the perturbation, excitations, I mean, is that something similar to what is known now, or it's not a solved problem?
I don't think it's quite the same, because this whole business with the linearization is you really want to get a constant coefficient equation when you linearize, right? So you could in principle have something with a Killing field, right? As you said, like you look at u divided by t, right? And that's your Killing field, but I don't think this has to be a constant vector field in space-time, right?
No.
So that would be like a more general symmetry, but that would not be the case where if you linearize about this, unless there are some constellations in some specific example, but because you want to linearize about something, end up with a constant coefficient equation, right? At least for this definition of mode stability that people are using, right? So of course, if you linearize about a general state, it could be something with a Killing vector field or not, you still end up with a linear equation. But in general, then it's not going to be a constant coefficient linear equation. So then you have to define precisely what you mean by stability in this case, and there are different definitions you can use, but that's not something that I've seen used in the literature in this context of stability. Stability here is something people mean something very restrictive. You linearize about a constant state, in the state where you linearize about has no viscous fluxes, right? You linearize about a state with zero viscous fluxes. And then you get this constant coefficient equation, and you look at the modes and you see if the plane wave solutions increase or not, right? That's something very specific.
Do you have a question, Jojo?
I have one more question about transport coefficients. Have you done any study of transport coefficients in your theory?
What do you mean by study?
Have you studied, for instance, viscous, or you have these non-hydro, modes? I'm assuming they're related to your, shear viscosity and bulk viscosity and all sorts of transport coefficients. But I was wondering, how do they change from or deviate from your from your known Israel-Stewart theory?
Okay, so what we know is that what George mentioned before is that if you look at the linearized theory, they have exactly the same thing, right? Modulo maybe some factors or something. It's exactly the same thing, and there are some constraints on this transport coefficient that come from causality, right? They cannot be anything, and that relates to what was mentioned before about the matching conditions. Other than that, we haven't done any kind of more systematic work. And now I don't quite remember. It's been a while since I looked at it. George, remember if Kovtun does that in one of his papers?
No, I mean, the statement is, so I think maybe what he's trying to ask is what happens to Kubo formulas. Is that more or less what you're thinking about?
I mean, for instance, like, if you look at the literature, there's a way to connect, I think Lee and Blasiu, they have like these papers where connect, your non-hydro modes to, transport coefficients, like C01. So now I was wondering, how does that change in your theory?
Yeah, we haven't done that. We haven't done that.
Okay.
Yeah, that's interesting. We haven't done that. Just a comment here. So Lorenzo, when you do this talking about the stability with the rotation, right? So you know there are a few subtleties here. So the way these guys prove stability, they prove stability using the energy function, right?
Yes.
And as far as I remember, I don't actually. That's a good point to see if the I think they had to assume that there was no vorticity in equilibrium, but I'm not sure about that. I'll have to.
I don't remember something like this. This is an interesting point you're making. I just remember that they were simply saying, I have an arbitrary equilibrium configuration given by the fact that I have a killing vector field and beta nu is...
But if you actually see what they do in the, so of course when you define equilibrium, we define saying that the beta mu is a killing vector, right? But when you actually see how they define the functional, for sure they linearize the theory around the equilibrium
they do.
But the equilibrium state does not have an omega mu. If you look at those equations, the equilibrium state does not have an omega mu in equilibrium, okay? So when you linearize around that, terms that would come with the vorticity, if the vorticity was there in equilibrium, I don't think they show up. So
I don't see where someone should see the omega mu. Actually, maybe I can try to take it now and I'll give a look. Because they were just saying, I have an arbitrary configuration, then I take an arbitrary perturbation and I see what happens.
Yeah. So it's, you have to see how they prove stability. It's proven through the functional, and you have to see how they linearize the equations around the thing, right?
Yes.
And I'm not sure if the assumption goes into that, but that's a good point. So in general, yeah, okay. So the functional thing one has to check again. That's a good point.
Yeah, because it's very interesting because their technique is simply saying, we proved that this functional is minimized in equilibrium, and we showed in our paper that this was equivalent to saying that the entropy is maximum in equilibrium. And in this sense, you don't, I mean, the killing vector field is arbitrary, and you just make an arbitrary perturbation, linearize, and check the sign of the whole thing.
Yeah, but for example, imagine that there was there was a term that goes with omega in the equations, right?
In Israel-Stewart?
Yes, in Israel-Stewart, right? So those terms, the problem is depending on the equations that they have, such terms would not appear, but they generally appear in this DNMR formalism.
Oh, I see what you mean. But
they don't. Yeah, some of them, yeah. That makes a difference when you do the functional. And the bad thing about the functional, even though it's very powerful, is that it's extremely hard to construct the damn thing out of the blue. We tried for almost a year to invent a functional way to prove stability for our stuff, and we couldn't. That's why we had to invent a new way to do it. But yeah, so there are some assumptions there, and the actual shape of the equations of motion and how you linearize around them makes a difference. So I would be a little bit more careful, but that's a good point.
Okay, I see.
So is there any other question or comment?
I have another short question, and I'm not sure might have been answered already, but if you go maybe back to the slide about the breakdown of solutions. So you said that due to your way of proving, it was not possible to infer the properties or the nature of the blow up of the derivative. So is there any other information you have about those perturbations that propagate, or maybe how, maybe you know how this, how the blow up might be generated?
Well, the short answer is no. And again, is a failure of the method, right? Because not another failure, but it's like a feature of the method. because approved by contradiction. So let me add one thing that I didn't get into when I stated this theorem. In fact, there's a dichotomy here that's not in this slide, but there are two possible things that can happen actually, right? So either the solution blows up in the sense that it's no longer what we call in mathematics a C1 solution. So it could, so one of the derivatives of one of the fields is blowing up, or the solution becomes unphysical in the sense that, let's say, for example, the pressure, the equilibrium pressure becomes negative, right? And of course, if something becomes unphysical, just throw it away. So if you restrict to physical solutions, then for this initial data, the solution cannot exist for all time as what we call a C1 solution, which means that some type of singularity has to be forming. But other than that, we can't really say anything about the nature of the singularity. And let me make another comment. Even for Euler equations, the ideal case, that turns out to be a very hard question. So the breakdown of solutions for Euler equations has been known for many years, going back, I think, started with the classical Euler equations, the work of Sideris, I think in the 80s, and then people like, for example, Shadi and Guo have done something similar for the relativistic Euler equations. But all these sort of breakdown results typically are of this nature. They are results that derive a contradiction. If you want to actually say something about the nature of the singularity, you have to do some much harder work. You can look, for example, for the case of the relativistic Euler equations, you can look at the work of Demetrius Christodoulou. So he has a monograph on shocks for relativistic Euler in 3+1 dimension to give an idea of the kind of techniques that are needed. So if you want to characterize the singularity, it's actually generally much harder. If you're doing things in 3+1 dimension, if you're doing things in 1+1 dimension, you might get away with some of the technical stuff.
Thank you.
So, any other questions or comments? If there is no other questions, okay, I will stop the recording, and thanks, Marcello, for the very nice talk.
Thanks for the very nice discussion.